Hello, welcome to the course on special relativity. Today we'll talk about Cartesian tensors, and specifically we'll consider coordinate transformations in 3D Euclidean space. First of all, consider a point P as viewed in two different coordinate systems S and S prime. Now S prime is ahead of S by a distance a along the x1 axis, which is common to both frames of reference. This represents a translation along the x direction by a distance a. The coordinate transformations relating the coordinates in the two different frames are given by these three equations: x1 equals x prime 1 plus a, x2 equals x prime 2, and x3 equals x prime 3. It is evident that these equations are not homogeneous, and translations are therefore an example of non-homogeneous coordinate transformations. Now let's take a look at another kind of transformation, which is known as inversion or as the parity transformation. To start with, the coordinate frame S is right-handed. What does that mean? That the unit vectors I, j and k are oriented such that I cross j gives us k. Now the inversion inverts the sign of each coordinate of a point P in this coordinate frame, and the coordinate system S prime will now be left-handed, which means that I prime crossed with j prime gives us, instead of k prime, minus k prime. Our third example consists of rotations about the x3 axis, which is the same as x prime 3. Here we have written the transformations of the x1 and the x2 coordinates related to the x prime 1 and the x prime 2 coordinates. And this is how the coordinates look like. In addition, we may have changes of scale or dilatations. Also, we can have oblique coordinate systems such as this one. Now, all of the above are examples of linear transformations. An example of nonlinear homogeneous coordinate transformations would be as follows: x1 equals x prime 1 sine x prime 2 cos x prime 3, x2 equals x prime 1 sine x prime 2 sine x prime 3, x3 equals x prime 1 cos x prime 2. For our purposes, we confine ourselves to linear coordinate transformations, which can be represented as below. We can also write this in short as follows: x1 equals rij xj prime summed over j from 1 to 3, and similarly in index notation. The big advantage of doing this is now that we can extend this to an arbitrary number of dimensions. Using the Einstein summation convention, we can write the first equation of this system as x1 equals rij xj prime. To remind you of the summation convention, now I'm not referring to Einstein in the hope that this will scare you less. Summation is assumed for any index that is repeated, and this index is called a dummy index. Now, if we want to suspend summation in a repeated index, we have to put it in brackets. For example, what we have written here, x1 equals ri j in brackets and x prime j in brackets, means that there is no summation. It is just a single term. More generally, we can write this as xi equals rij xj prime, with I and j running from 1 to 3. Since j is repeated in one term, summation occurs over it. It is called, to repeat what we have said before, a dummy index. I is not repeated and is a free index here. We can generalize this to n dimensions by letting I and j run from 1 to n, where n is a natural number. In matrix notation, we have this as column vector x and x prime, suppose. They are related as x equals the matrix R into x prime, column vector. Transposing this equation, we get x transpose row vector equals x prime transpose row vector multiplied by R transpose 3 by 3 matrix.